Welcome to PASCO Spectrometry webinar. We'll spend the next hour exploring how to use the wireless Vis sensor, as well as the UV-Vis. And we're also going to be collecting lots of data and looking at save files for biology and chemistry investigations. We'll start off by using the wireless Vis spectrometer. And then we're going to begin by looking at colored solutions, reviewing how spectrometers work. And then we'll look at the fluorescent spectra of some compounds that are responsive to the two excitation wavelengths that are on that spectrometer, the 405 nanometer and 500 nanometer wavelengths. Then we'll apply Beer's law and use a few known, just several known solution concentrations, just blue dye to create a calibration curve that not only is going to allow us to identify the concentration of an unknown concentration of a blue substance, but also we can use that data, the concentration data, to map the change in a solution's concentration over time as we undergo a bleaching reaction to make it from blue to colorless. And then we can study kinetics that way. So not only are we going to be looking at kinetics of dye bleaching, we're going to look at some data from an enzyme catalyzed reaction that does the opposite. It goes from colorless to colored, going from clear and colorless to a brownish color solution as the reaction proceeds. That's the peroxidase reaction with hydrogen peroxide and glycol. Then we'll switch to the UV-Vis spectrometer to look at colorless solutions and see how the molecular properties influences absorbance patterns. We'll revisit Beer's law and look at how can you use UV data to model disease transmission and contact tracing. And finally, we're going to use the available fiber optic accessory cable to study the spectra of light sources, including not only the gas discharge tubes, but also flame tests with birthday candles, special birthday candles that are colored. Now, while we go through all these things, I'm also going to demonstrate both, not only just both our spectrometers, but also both versions of our spectrometry software, the Spectrometry app and Chemvue. And we'll be answering your questions if you're here live as we go along. And I'm also going to be saving files, opening files, talking about which platforms are supported by each app, and point you to some resources for experiments as well. Okay, let's get going now. So let's just do a quick review of transmittance and absorbance. I'm going to start with that wireless spectrometer. I'm going to switch the camera to it. And first of all, the graphic is an indicator of how this spectrometer works. You see the graphic of the little light bulb here. That is the light sources on this side. Light passes through the 1 centimeter, a little bit larger than 1 centimeter aperture, so that our cuvettes fit in there. To the other side, to the detector. So this is where the detector is. You want a clean path of light coming through here if you're testing solutions. And then here's the cuvettes that come with the spectrometer. One side has lines, the other side is clear, so that you can always pick up the cuvette by the line side and not worry about wiping fingerprints constantly with your Chem wipes. With that in mind, you want to remember that you are going to make sure that light has a clean path from the source to the detector. So you hold the cuvette by the line side and place it into the spectrometer with the clear sides through the light path. Okay, that's my blank that I just put in there. And I'm going to start out with some colored solutions. And these are dissolved in distilled water. So my solvent is distilled water. That's what my blank is, so that I can erase any background noise from just whatever's in my solvent. And we can look at just the solute. So this spectrometer is most useful when you're working with transparent colored solutions. So let's start by talking about transmittance. Okay, transmittance. So something that would help my students remember what it is. Transmittance is the wavelengths that go through the solution. They travel straight through and make it to the detector. And it's measured directly as a transmitted light and translated to a percentage in the software from 0 to 100%. Now, the absorbed light, that's what absorbance is. It's absorbed and blocked. So if we see a blue solution, we know that blue light is transmitted because that's what got through. I can see the blues, but a lot of maybe some blue light, but maybe and a bunch of other colors could be being blocked and not coming through. The blocked colors, just as transmittance and absorbance are the opposite, so we can think of colors the same way. If blue is transmitted, then the opposite on the color wheel is absorbed. Orange is absorbed. That's what I can use this wheel for, is to predict. I see blue light is transmitted because it's a blue solution. I can predict that orange is absorbed because it's the opposite of what's transmitted. And now we can use a spectrometer to see if that holds true. So I'm going to start with the Spectrometry app. And there, like I said, I was going to use Chemvue and the Spectrometry app. Let me drag that over so you can see it. There it is. Okay. And I've currently got, I accidentally left my UV-Vis spectrometer plugged in. So let me close that program and reopen it here. There we go. And on Spectrometry. Okay, so here's that app. Now I have this exclamation point here because I don't have any spectrometer connected. And when you first open the software, it warns you, you need to connect a spectrometer if that's what you want to do. You could also go straight to opening a file, but we're going to collect some data to see if it's true that blue light's transmitted and orange is absorbed. So I turn on, I have a wireless PASCO spectrometer, so I can connect it via Bluetooth. If I go to that triangle, that's where I would be doing the connection. I'm going to choose my wireless interface. My spectrometer is in Bluetooth searching mode. It's on and the blue light's flashing. I can see that I have more than one spectrometer here. The one with the dash, I have the 6-digit code on the side of the spectrometer, and I can match it up to the 6-digit code here and hit connect. Now these other two, the numbers look slightly different. They're older generation spectrometers that connect via traditional Bluetooth, where you have to go through the settings, but our current model can go straight in the software, connect via Bluetooth. So, let's say that I want to start recording data right away. I'm just so curious about my data, so I'm going to hit the record button, and I see a little eraser icon. That's probably only on my screen, but it reminds me. Oh wait, you can't just start collecting data. You've got to calibrate. You've got to cancel out anything that's in your blank. You want to get rid of all the noise from the solvent. So we have to do the calibration. First, we're going to calibrate dark. It reminds you if you forget. And then we're going to calibrate the reference. And now I've done a calibration relatively quickly. We recommend you let your spectrometer warm up for 5 to 10 minutes because that light, it's a light. Even though there's LED, you still want it to run long enough to get to its highest, what's the word I'm looking for? Intensity. Because as it's warming up, it will change its intensity. So the thing we're looking at, though, we're just looking at colors. So, I'm not really that worried about accuracy, so I'm just going to quick do a calibration and then move forward. We'll recalibrate it when we're ready to do a quantitative analysis. Okay, so the prediction was we are going to see the blue is transmitted. We think that orange is absorbed. By default, it shows absorbance first. And I can scale with this button, the auto scale button, and I can see the highest peak here for the measurement absorbance is indeed orange, and the lowest peak is indeed blue. Blue is least absorbed, but right. Blue is least absorbed, but orange is most absorbed. And then there's transmittance. If I just tap that measurement, I can swap to transmittance and then rescale and see that it is the opposite. That's the opposite curve, right? I can use the tool on the bottom right here, this add a y-axis button, to show absorbance at the same time. And now I can really see that absorbance and transmittance are indirect opposite of each other. So then, well, why are we bothering to start by showing just absorbance if transmittance is the thing that this instrument measures? And the answer is because the math works out more easily when we work with absorbance rather than transmittance, because it gets a bit messy when you're changing your percentages and it's just easier math. I'm going to turn off the y-axis for transmittance and now only look at absorbance. Okay, so we are looking at blue, and according to the color wheel, orange was the most going to be the most absorbed substance. Now let's look at yellow, or color rather. If we're looking at a yellow, we know that yellow is transmitted. We can predict that violet is going to be the highest absorbance, and let's see if that's true. Let me scale. And sure enough, look in this blue-green region. I'm sorry, blue-purple region. That is the highest absorbance, where yellow is on the low end of absorbance. So if that's true, then if we have a green solution, this green, right, we would expect red to be the highest absorbance. Is that true? Kind of, yes, but also blue's in there too. But remember, if we look, I'm going to hit stop. And if I hit stop, I've now recorded this run. I'm going to scale it. And I can rename it as a green solution. That's what green looks like. We expected red to be the big peak, but we've got a lot in the blue and violet as well. Let's see why. Let's go back to our blue and record it. Okay, I'm going to scale. I want to see everything at once, right? So I'm going to hit the show all runs button. And I'm going to rename this blue. And now let's do the yellow. And then scale and stop. Rename this as yellow. Okay, and show all the runs. And green, that's this run here. It is the overlap of what blue shows and what yellow shows, and that makes sense because yellow and blue make green, right? Another solution we can look at, we know that green's a mixture because we see that it's a combination of yellow and blue. What if we want to study some biology and look at maybe an extract from a plant? This is from cilantro in my fridge at home. I just smushed it up and did a very simple filter. I just smushed some cilantro leaves in some distilled water and pushed the solution through a coffee filter. So it's a very crude extraction, but it is an extraction nonetheless. It's a very light green solution. And this is from a plant. So that's what cilantro looks like. It's a green solution, so it looks a lot like my green dye. It's got a big peak in the red, big peak in the blue. And I'm going to rename this cilantro. And then let's take a look at a different plant. Usually I do spinach, but I didn't have any of that in my fridge. I had spinach and lettuce, so I mean cilantro and lettuce. So let's see what the lettuce looks like. This is a romaine lettuce. So it might be fun to do different types of lettuce and different leaves. And I'm not really worried about what the absorbance values are. Typically, your ideal absorbance values are between 0.1 and 1. That's where you want to be if you're doing a quantitative analysis, between 0.1 and 1 on absorbance, because you're getting 90% of the light coming through that's being transmitted, and that's just the most reliable data. Now, I see kind of the same thing on my lettuce as I see on my cilantro. Let me zoom out so everything's showing up. Bunch of information here shows me that green is a combination of the components of yellow and blue, but also, let me turn off I can delete runs if I don't want them anymore. Let's get rid of the dye, food dye, and looking only at plants, extracts from plants, and this one is my lettuce. We see something very interesting here. Peaks in the same place, different plants in the red and the blue. Green plants contain chlorophyll. So what color is chlorophyll? It's green. Why is it green? Well, let's take a look. It has to do with the molecular structure, and we'll talk more about double bonds and the colors that you see in a minute. But we have other data that verifies that the high peaks we're seeing in the blue and the red, those are chlorophyll A and chlorophyll B. And we also have a mix of carotenoids in there. That's why we see kind of a continuous hump through from the 400s and up to the greens. Those are the carotenoids, and they all combine. Oh, another time. Thank you, Windows. Wants to restart my computer right now. So we can take that extract and we can do a chromatography experiment. We can cut out these portions of the chromatography paper and re-soak them in a solvent, and then make a solution and stick them in the spectrometer, and that way we can separate out our chlorophyll A, chlorophyll B from our carotenoids or xanthophylls. So this is the one way that you can isolate pigments from plants and get their specific absorbance spectra on the spectrometer. So there's a biology application. Then there's fluorescence. Our spectrometer, wireless spectrometer, also handles fluorescence. So I'm still in the Analyze Solution tab here. I just switched to fluorescence 405. I said that there are two excitation wavelengths. There's 405 nanometers and 500 nanometers. So one of the most common substances to study is fluorescein or fluorescin. It's like potato, potato. So this is a very concentrated solution of fluorescein. And I'm going to turn on the fluorescence at 405 nanometers. I'm going to start recording data. And before I stick that cuvette in there, I want to point out, you can see right now, to see the purple inside of the spectrometer window. I'm going to hit stop. Okay. You can see that there's a purple light in there. And actually, the purple is right here where the purple icon is. And you're seeing the reflection of the purple light pointing that way. So the excitation wavelengths are perpendicular to the detector, so that way any light or the majority of light coming to the detector is not from a direct line of light coming to it. It's because something fluoresces and excites and then drops back down to the ground and releases the photon at a different wavelength if it is excited by that 405 wavelength, if it's able to absorb and then re-emit at a different wavelength. So let's see if that happens here. I'm hitting start. And I'm going to scale because it looks like it's barely anything, but here, oh, look, I've got a blue color on the run. So let me hit stop. If I don't like the run color, I can always just hit start again and see if I like that color better. I do look kind of like this brown better because I could see it on the screen better. So this is the 405 nanometers. I can see that's where it is on my wavelength here. Let me full size the screen here. And since the light source is perpendicular, I'm going to go ahead and turn my cuvette 90 degrees as well. And I can already tell before I even finish putting it in that look at that fluorescence on the spectrometer. And we can see the wavelength shift. Yes, the 405 went down because it's being absorbed. All that energy is being absorbed and being re-emitted at a longer wavelength. So every time you see excitation, you're going to see it re-emitted. If it's re-emitted, if it's absorbed and it re-emits in the visible, it will be a longer wavelength, lower energy. So there's definite evidence of fluorescence from fluorescein. It is definitely excited by the 405 wavelength. Okay, so there's that. And now I could also rename that fluorescein too. Fluorescence also is 500 nanometers is another option. Let's go back and look at plants in the form of olive oil. I've got olive oil, which is one of the darker oils. We're going to come back to olive oil when we go to the UV-Vis, but let's take a look at the fluorescence here at 405. So let's see if we get any. Okay, I haven't even finished putting in the spectrometer, but look very carefully at the cuvette. You can see that it just turned red. The whole solution turned red, and that is the emission. The emission's in the red. I have evidence here that's being re-emitted at red because 405 was absorbed and we're re-emitting in red. So that's happening because there's chlorophylls in olive oil that are still there, especially extra virgin olive oil that's quality. You can bring your laser pointer, one of the blue ones the laser that's set to 405 nanometers, and take your laser pointer to the grocery store and stick that laser pointer through the olive oil bottle and see if it turns red. If that would work on a clear bottle. If your olive oil turns red, it's really fresh and it is extra virgin olive oil because there's lots of chlorophyll in there still. Cheaper olive oil, maybe not so much, but there's one way you can evaluate. Does it fluoresce? It should, if it's fresh. Okay. All right. So that is fluorescence. Let me go back to the presentation briefly. Okay, it's time to do a Beer's law. Now, Beer's law is applicable for any time you want to know the concentration of a solution, whether it's because you are, oops, I clicked the wrong button, whether you are caring about the actual values or not, but it is a quantitative analysis, so you do have to do a little bit more work here. We're going to go back. We're still in analyze solution. We haven't moved to the new tabs yet. I'm just going to leave this application, spectrometry, because I said I would also show you Chemvue, and I'm going to work in Chemvue from here on out. And I'll talk about the difference between Chemvue and SparkView. I'm sorry, Chemvue and Spectrometry app later on. So this is what Chemvue looks like when you open it. It's not as colorful as Spectrometry, but it's pretty darn amazing, the things that it can do. So I'm going to go, the first thing you do in Chemvue is you go to the Bluetooth connections. And there's that spectrometer. It came up. I'm going to connect it. And I'm connected. And there we go. There's that familiar rainbow. It's got the same buttons. My calibration is down here, calibrate dark, calibrate reference. I still have the icon to add the y-axis. I still have the same icons that I didn't talk about yet because they didn't apply yet, but we will talk about them in a minute. There's a scale button. I still have smoothing and scans to average, which I haven't talked about yet, but there's even more buttons here. We are on the Analyze Solution tab, and sorry about my giant hand covering up the little notes here. I just happen to have a giant mouse pointer. Typically, you can read the labels on your own version of your device. So first thing I'm going to do is going to recalibrate, because remember I said that I didn't let the spectrometer warm up long enough. So there's my blink. Oh, actually, you know what? All of my solutions were made on a different day, so I got that specific distilled water I used on that day and made that my blink. So let me just hit the calibrate dark button, and this will do the same thing. If you forget to calibrate, it'll remind you need to calibrate first. And now I'm calibrating the reference. That's my blink. And we're going to do a bleaching, first a Beer's Law plot, and then we're going to bleach this blue dye. It's the same blue dye we just looked at a second ago. So now that I'm calibrated, after I let it warm up, all I did was I got some dye, food coloring, and I put 1 drop in 100 milliliters of distilled water, and I checked it to make sure that the most concentrated solution, let me scale this, was below the absorbance of 1 and a pretty good value, so I could do several dilutions and still be above 0.1. So again, the range between 0.1 and 1 when you're doing quantitative analysis, which we're about to do. So the first step here, get your most concentrated solution, make sure it's within that range, and then hit stop, because first thing you need to do is pick an analysis wavelength. You want to analyze at the highest absorbance, so you're going to touch the point that looks like it's the highest, and you can turn on the wavelength selection tool, and there is the coordinates for that point. You saw those buttons just disappear. If I want to bring it back, I can just click that bubble again, and I can hit the check mark to select that. I can also move it left or right if I want to nudge it to make sure I get the absolute highest absorbance. And like I said, my mouse pointer is blocking the value, but that's just because mine is giant. So it looks like 9.08 is my highest absorbance, and 0.908 rather, and that's at 620.961 nanometers. Or if I wanted to, I could also just type that in. Let me hit the check mark to keep it. Okay. I'm going to now that I have an analysis wavelength, I'm going to do a Beer's Law plot, and that's the second tab, solution concentration. So that's why it's a table and a graph, and it's automatically set to manual sampling, which means it won't record the data point until you tell it you're ready when you hit start. So I'm just going to go ahead and hit start, and I have to hit this check mark when I want to keep that value. All these concentration values are editable. I'm just making up a fake concentration because it's easy for me to just call my solution 1, but you would put the actual molarity of your substances here if they were known. And I do know that I've taken my dye solution and I've reduced it down by 1/4. So I know that the concentration is 0.75. And then I diluted it in half and I got 0.5. I just did some serial dilutions, going in halves, in halves, and halves. Okay, and finally 0, I'm going to use my blank for my 0 concentration. My molarity of 1 has an absorbance of about 0.90 rather. And then I'm going to check the absorbance of my 0.75. concentration. Then you can see the graph is developing as I keep each data point. And you might be thinking, oh, I hate that the lines are connected. Don't worry, you can change that in Chemvue. That's a preference you can set, and I'll show you how to do that in a second. 0.13. And we're going to keep that. And now we're going to do the blank as my 0 concentration. So you can already see that my data is looking nice and linear, but I haven't hit stop yet because first I'm going to scale. And you know what? This rainbow is nice. It shows me what the analysis wavelength is, but it's in my way. So I'm going to turn it off by hitting the show scan live display button. That's something that you can also do in the other Spectrometry app besides in Chemvue. Now I said that you can set the lines to be not connected. That's in your preferences here in the main menu. Preferences, under graph preferences, you can turn off show connecting lines. And you know what? Maybe it's hard for you to see this green. You know, so I could also change the run color if I wanted to do that. And I could also, you might have seen that there was dark mode in here. Let's very quickly turn on dark mode. Check it out. Now I can see that green a little bit better because the dark mode is on, right? So I'm going to leave it in dark mode too. That's another option besides changing run color. So now I have my data plot. I'm going to hit stop. And I'm going to turn on the linear fit. And I'm going to rescale. I'm pretty close to the origin here, right? With that fit. It looks like it's a decent fit, but I can use the line equation y equals mx plus b, the slope of 0.906. B, the y-intercept, is really close to 0. And the R value, 0.996, the closer that is to positive 1, if it's an increasing graph like this, or negative 1, if it's decreasing going the other way, that means it's pretty linear, and it's a really good fit if not only visually you see that it looks pretty good, but also the root mean square error, which doesn't show up in spectrometry, the RMSE. The closer that is to 0 means that's the detail of how far away are the dots from your predicted line. The closer 0 to 0, the better, because that means they're not very far away if it's really close to 0. So that's another way to analyze and evaluate goodness of fit here with a linear fit. And your data needs to be linear. And that's, again, why we want the absorbance to be between 0.1 and 1 of all your samples, so that you can indeed stay in the linear range for the instrument. My concentration is automatically on my x-axis. And now that I've mapped the concentration to the absorbance, I can use that for a time concentration over time analysis or a kinetics experiment. Let me go back briefly to that graph that we had. Are there any questions that I should address, Mike or Roger? Nope. Okay. I'm just talking really fast, so my apologies, but moving on. So we got this linear fit. We got the Beer's Law plot. We are going to look at some other tools that I haven't touched yet, like the add note to point. So let's say that I have this slightly outlier here. It is just barely outside. I'm not sure. Maybe I want to investigate my solution and make a note that I think it might be an outlier, but I don't know. I'm pretty happy with the data. So the outlier is, I was able to use the arrows to move it to the point that I wanted. That's where the outlier is. That note is directly on that data point there. So that's what that add note to the point button is. And if I don't want it, I can just retouch the button, change it by editing it, or I can get rid of it with remove. Okay, let's go to figure out an unknown. Now I'm going to start recording data. My linear graph is still on there. I'm going to switch to the down here on the bottom left, the unknowns table. So what that lets me do is it lets me put my unknown solution in and measure its absorbance. And the absorbance is 0.442, and then I can hit stop. And that value of 0.442, well, there's a few different ways that I can figure out what is the concentration based on the absorbance. I can do an educated guess by doing a little bit of a manual scale on the y-axis, and I can maybe see where 0.44 is. Oh, that's probably right around here. And if it goes straight down, that concentration is somewhere between 0.4 and 0.5. Okay, so that's one way I can do an educated guess. And I could say, oh, I think it's 0.45 molar. And then it put the dot for me here. It's green. That means, hey, that's a pretty good guess. Let me show you how the guesses or the guessing or the X and Y points work. If you have a green circle that's lighter green, that means you're below 5% error. The lighter the green, the closer to 0. If you've got a square, you're between 5 and 10% error. The browner means the more close to 10%. The yellow means more close to 5%. And if you have an X, you're just way off. So if you have a real wild guess on the concentration, like, oh, I think it's 0.6. It's really wrong. It's way off that linear fit, and here's the X to show it. So, so those are a couple ways you can use a wild guess. You can do an educated guess. You can rearrange the slope equation. You're given y equals mx plus b. If we look at the y and x, y is absorbance, x is concentration. If I plug in and rearrange, I want to solve concentration x. Then I just subtract out my y-intercept from my absorbance value of 0.442, and I divide by slope. So if I do that, let's see, my absorbance value was 0.442, and I'm going to round the B. B value is 0.256. It's 0.256. 0.256, and then divide by my slope 0.906. That says 0.4596 is should be my concentration, my X. Let's see if that's true. Oops, I moved the wrong thing. There we go. 0.4596, and it rounds it to 4.6. And look at that, it puts my dot, I'm perfectly on the line, which I should be because I used that linear fit equation. So that's another way to get the unknown concentration using the software. You could also look at the proportions of the concentrations to the absorbances and set up a proportion for your unknown. For example, the concentration of 1 to absorbance of 0.897, you could set up like this. So the ratio of the known molarity over the known absorbance, set it equal to the unknown X value over that known absorbance of 0.4, I already forgot what it was, 0.442. 0.442. Okay. And when we did the educated guess, we did this already, move the graph to find the X coordinate at the absorbance. Okay. Any questions to address, Mike? Nope. Okay. Alrighty. Moving forward. Now, I said we were going to do kinetics. And I also said that because we did this Beer's law curve, we can map, we've got already the map of the absorbance to the concentration. So we can actually interpolate the concentration values as time goes. Now, you don't have to do this step because when you go to, as long as you've gone to your solution spectra page so you could get this analysis wavelength, as long as you've done that step, you can go straight to time. But if you have your Beer's law done, you might as well change your Y value by clicking to get the concentrated or concentration. Whoops, I keep doing that. A happy mouse here. There, okay. You can toggle that to the mapped concentration and it'll tell you, it'll interpolate those values based on what you told that those concentrations were. So let's take the original, this was my starting out concentration of 1, quote unquote 1 molarity. Blue food coloring. You can do this with, the copper 2 sulfate as well, that reaction. You can do, I'm sorry, not copper 2 sulfate, the crystal violet. It's one of our labs in our experiment library. I'll talk about that in a second. So we're going to do, this is bleach. I just got in a pipette. I'm going to put a few drops of bleach into the cuvette, not on the spectrometer because we don't want to spill stuff on it. And then I'm going to quickly close it, flip it, mix it a few times, to invert it to mix it, and then set it in here and start right away recording. And let me get that going. I just put like 3 drops of bleach in there, seal it, fully invert a couple of times, and I can already see it going, so I better hurry, get it in there, and then start recording. Okay, and I'm gonna scale it. So now here's where I regret, oh, I should have turn line back on because it'd be easier to see the line. And you know what, while it's running, let's see if I can do that. Graph preferences, let's turn those lines back on. There, okay. Now I can see it better. And yeah, that reaction's going, and I'm gonna let it go for a couple minutes. But if you happen to be getting a really slow reaction, here's what I recommend. Like, I like to, so if I started at, if the first data point's close to 0.8, I want to at least let it run through a half-life. So get down to the half of that concentration to 0.4. If it's going real slow, let it at least go to 0.4. But I like to get 2 minutes of data either way. So I know I'm already gone through a half-life here. It's a really fast reaction, right? Meanwhile, while that's waiting for the next minute here, I'm going to get this bleach reaction going in the test tube so you can kind of get an idea of what's happening. This is what you would your students. Put some bleach in. Ideally, you would have a cuvette with the same amount of blue dye, and you would add the same amount of bleach, so they're perfectly comparable, but that would be hard to see here on our webinar. So I can see that the color's fading, may be harder for you to see, but there it goes, going away. And we're going to go till 120 minutes. Okay, and we're going to later, after we finish the run, this is almost like the bottom's already clear on my test tube. So it's always nice to show students the reaction off to the side. So we are going to go for another 30 seconds maybe. But yeah, we can figure out the reaction order very easily with we're going to linearize the data or figure out which version of the concentration values would be most linear, whether it's the actual concentration values or the inverse or the natural log. And the software does that very easily. Okay, that's enough time. It's been 2 minutes. I'm going to hit stop. So let's turn on that linear fit and see if this is a zero order reaction because this is just concentration. Nope, probably not. But let's look at all the runs because that just doesn't look like a good linear fit. I mean, my R value is real close to zero, -1, but visually I can see it's not a good fit. Well, it might be, we'll see. It doesn't look good to me though. Let's go to the quick calcs here and change now. Let's look at the natural log of the concentration, and that looks all right. Not terrible. Similar R value, but visually we can see it's a better fit. And now let's see the inverse. Nope, definitely not that one. So it looks like it's a first order reaction because the most linear form is the natural log. So now we also have the linear fit. We've got M, the M value can be used to figure out the pseudo rate constant. Let's look at this. So we determined it was a first order graph because the natural log of these orbits was the most linear. In that case, we take the slope and add the negative to it to get our pseudo constant. So K in this case is -M, negative slope. So that's how we use the software to figure out order in kinetics. And for biology folks, let me go back one. For biology folks, let's look at a famous AP biology experiment for enzyme action. Let me bring that, or I'm opening it in the other application in spectrometry. So this was the peroxidase glycol reaction. And what we do is we've got a colorless solution that turns color. This lab isn't available in our experiment library, and I'll talk about experiment library in the next slide. We pick an analysis wavelength at 470. We don't have to do a concentration curve. We don't need to do Beer's law because all we care about is, does peroxidase catalyze the reaction and what's the initial rate compared to later on? So we can see here that there are tools that you can use in spectrometry. These are available both on both versions of the application. This is the selection tool right here for this version of the app. So I selected this portion of data. So I'm looking at the first minute and I apply the slope just to the first minute of data instead of the whole run because it's clearly not linear. And that's telling me that the slope or the rate is 0.00405 for the first minute. But then if I look at the next minute, it's slowing down for sure. That's lower and lower every minute that goes by. So we are losing the glycol and it's being converted to the tetraglycol. And while that's happening, we're getting the color, the brownish color show more and more and more. So it's kind of the opposite of what we just saw. This reaction takes kind of a long time to set up. And that's why I did the blue dye live. But the peroxidase is an application of kinetics in the biology world. but it's the same idea. So student-ready experiments in the experiment library. You can go to pasco.com/freelabs or portal. If you're a portal subscriber, you get a little bit more on the file side. You get the teacher answer key, an editable form of it, and the student file in an editable form, and oftentimes free data sets, depending on the lab. So hydrogen emission and absorption spectra is one of the examples of the experiments that we have in the experiment library, along with aspirin analysis for the UV-Vis. We're going to switch over to the UV-Vis and momentarily close out of. Okay, something I need to mention before I go into the UV-Vis. So we've been doing Chemvue. We've been working with Chemvue, but with the wireless spectrometer. Now we're going to switch over to the UV-Vis spectrometer. We have to completely close out of the Spectrometry app or Chemvue, whichever one we're doing, because when you connect a spectrometer to the software, it has to like kind of reorganize and be like, oh, you're using the UV-Vis. Let's set up for the UV-Vis. You can't swap to the wireless in the middle of a session. You have to save your work and close and go to a different session in your app. As you have to basically, you can only do UV-Vis experiments moving forward if that's the first thing you connect. If first thing you connect is the wireless, you have to keep using wireless until you save your data, close it, and reopen a session. Any questions, Mike, that we should? Okay, all right. So I've got Chemvue open again. Here we are at the main screen of Chemvue. And now I'm going to plug in the USB connection. So the UV-Vis is not wireless. You need a USB. And it does not have fluorescence, but it does have a much bigger range of analysis wavelengths. I'm sorry, bigger range of wavelengths. So you can see how low, far down it goes into the UV. It's somewhere in the 180 range on the minimum, all the way past 1,000. So this is the range of the UV-Vis spectrometer, much bigger. And as soon as I plugged in the USB into the computer, it immediately went to this page on its own. So it's smart. Okay, so we're going to, let me bring up that PowerPoint here. We talked about that already. So this was the guaiacol reaction. It starts out colorless and turns colored because we get this major complex, large polymer that has a bunch of double bonds, and it's very highly conjugated. And that's why it goes from clear to brownish, because of the more and more and more and more conjugation. The more double bonds you get, the more you're being pushed to the longer wavelengths. And as you push from UV into Vis, you start seeing color. So that's one of the molecular properties you can get from seeing the UV portion of the data that you wouldn't see with the wireless. So let's real quick talk about the two different spectrometers. The PS2600 is the wireless one you just saw. It's the one with fluorescence. You get 10 cuvettes that are polystyrene. So these cuvettes, since they're polystyrene, you can't use like acetone, but you can use dilute ethanol and water and those kinds of solvents, but just not acetone. And there's an optional fiber optic cable accessory, which is different than the fiber optic cable accessory, or rather for the UV-Vis. This is a quartz fiber optic cable. They are not interchangeable between the spectrometers. And they're separate purchase. They have their own part numbers. On the UV-Vis spectrometer, the range is much larger. Just go to the product pages to see what are the specs on each, what are the ranges, what comes with each of them. So you get these micro volume cuvettes with the UV-Vis spectrometer. They come 10 in a pack. And you can optionally purchase a quartz cuvette because, like I said, it goes down to the 180 range. And if you're lower in the lower part, like over here, those micro cuvettes are good. Oh gosh, I can't remember off the top of my head. If Roger, if you could put that in chat, the lower limits of these quartz is what you're going to want to use if you're going down.
It's about 230, 230-ish.
Wavelength. Okay. So if you scroll down to the bottom of the product page, you also can see the accessories that you can get or you can see the opposite other spectrometer. So that's a screenshot of what you get at the bottom of the page if you go to the link to the UV-Vis spectrometer. Okay, we're going to talk quickly about a disease transmission simulation. I'm going to switch cameras back to one. Okay. So first of all, let me grab my tonic solution. I'll be right back and grab that. There, got to bring that over. Okay. So this is tonic syrup. So it's different than tonic water you get from the grocery store is 1/5 of the concentration of this. This is 5 times more concentrated. So it's like super bright. So use this very concentrated tonic syrup, and I got this one from Top Hat Provisions. Oh, I'm sorry. You can see that better. And they're really close to us here in Roseville. They're in San Francisco. So the day before, you're going to create a calibration curve. So let's open up the calibration curve that I did the day before. So here's, you can save files, you can open files and exchange files. I'm going to open. I don't worry about the data that's on there right now. Got a file on my desktop. I think it's on my desktop. Let me find it. Oh, there it is. I'll open in the other app so I can keep the UV open right now. Okay, here's my data. So I just did, so here's what I did for that. I don't really know what the concentration is for this. I mean, I could call a company and ask, but I don't know. It's not on the bottle. So what I did was I looked to see how concentrated is it just without diluting it. So I put the sample in the UV and look at this big signature we get down here in the UV range that we'd never have seen on the wireless version of the spectrometer because it doesn't go, it stops around 4 in the high 380s, or 390s rather. So this quinine actually fluoresces about 350, or rather absorbs at about 350 nanometers. But that's not the analysis wavelength I picked. I picked something, it only had an absorbance of 0.5, exactly where quinine was. So I just picked a spot a little bit higher up, just below the absorbance of 1, to see if that would be linear. If I took and made some serial dilutions. And sure enough, I did that. I made some serial dilutions. I did kind of the same thing I did with the blue dye. I did a quarter, a quarter, a quarter, a quarter, more and more dilute. And it sure enough, it was linear. And that allowed me to make a calibration curve. So how do I use this? Well, here's how you do the activity. So those of you who have done this type of activity, you know that you give a test tube to each student, same volume in every single one. Usually you do this with like phenolphthalein, like an indicator with acid, but you don't need to have goggles for this version because everything looks clear to begin with. All these test tubes look perfectly clear. But one of them is quinine. It has got quinine in it, and because quinine fluoresces, so you can tell which one is the disease test tube. So here's a funny twist, right? COVID, your folks were grabbing quinine as a treatment, but in this case, we're using it as the disease model, as the disease agent, or the infectious agent. So you can see who patient 1 is. It's going to be student number 5, whoever gets this test tube. All the other students are getting just distilled water. So the way that you do this is you have students walk around the classroom and you tell them to stop, and then they swap with a person they're near, and they kind of do this. They just, whoops, and they don't spill on their keyboard, hopefully. They fully mix the solution one time, one to the other test tube, and then a second time, one to the other. And now you've got a 50% dilution on the first round of meeting between students. And so this would model, if you had an infected person, this models the getting a contact with somebody who's ill or not, maybe not symptomatic yet even. So you can't tell because you can't see that they're symptomatic without that UV light. Then they go half and half back to the same sample volume they had before. You do that a second time, but you have students move around and they can't have the same partner twice. Then they swap, and then you do it again a third time. So you get 3 rounds of swapping. And once you got your 3 rounds done, then the students bring their samples to you. You put the, first you're going to do this with the UV light to minimize the number of times you have to take a sample on your spectrometer. And you can see, well, I don't see, you're perfectly clear. You're not, you have none of the infection. You passed the COVID test and you're negative. But if you have any indicator using the UV light, well, we have to test you now to do some further testing. Let's see what your absorbance is when we put your sample inside of the cuvette. And if the absorbance is above 0.1, you've got the disease and you're infected. If you're below 0.1, hey, maybe you're glowing, but it's not enough viral load to mean that you're ill or able to spread. So that's one way to model disease. You can throw in all kinds of things in there like student 16, stay home today. There's all kinds of ways you can modify this, but once everybody's got their, I'm going to switch cameras again. Once everybody's got their sample and you figure out who's infected, now you're going to see if any of the antiviral that you set up work. So I'm showing 2 test tubes here. Both are samples of, I think this was a second 50% dilution. So we're going to test a potassium chloride. I'm looking for it. What do I do with it? Quencher. So what's quenching? Quenching is adding a substance to a fluorescent sample that makes it stop fluorescing because the thing that you add absorbs that light and does not re-emit that energy at a different wavelength that's in the visible spectrum. So let's see what happens. We're going to see if quenching works here. I just put in an antiviral treatment. Is it working? Well, it is working because if we compare, remember they were both the same intensity. If we compare now, wow, I don't see any more glowing. It's gone. It's a cure. It's a cure. So you can do a placebo where you can put one substance that's not going to cause quenching and another that will cause quenching. And this is just potassium chloride KCl solid. It'd be better if you put a liquid in there because you could just put water as the placebo and you would still be getting, let's do that. Let's put in some water and it's diluting it, but you're still getting the glow. So not everything makes it stop glowing. Only the antiviral works. So that's a nice model of disease transmission, contact tracing, and and treatment. Yes, there's a question. What's the question? Do we have the wavelength of black light? Let's see. I think it's a 405. Let me check the flashlight. It says UV LED. That's what it says on it. I believe it's 405, but here we can test that. That's a great segue to one of the last things we're going to do, which is we can test it with the fiber optic cable. We can do that. Let's move on. I know I have just a few minutes left, so I'm going to kind of talk fast to get through these things that I promised I would say. So anyway, the Spectrometry app, it's free on these devices. Go, it only supports spectrometers, so you can't connect like any of the other wireless stuff to it. It's only for spectrometers. It's free on our website at pasco.com/spectrometry. Go there if you're not sure if your device is compatible. Mac, or rather iOS devices, only the wireless is compatible. So if you've got iOS, go wireless because you don't have a way to plug in your USB. Same for Chemvue, but Chemvue is a cost app, but it's very low cost. I encourage you to go see how much it costs at pasco.com/Chemvue. It's right now $1 per year. It's low cost. But if you have Portal, it's free. Anyway, it's the same thing in Chemvue. If you have iOS, you're going to want the wireless. But Chemvue isn't just for spectrometers, it's for all the things, all the chemistry things, including the melting point apparatus. Is one of my favorite apps. Oh, I wish I had time to talk about that today, but that's not what our webinar is about. But Roger will be talking about it in a future webinar. Anyway, like I showed you, the data displays are smart. You plug in the instrument, it already knows what display you want. So those are the benefits of the Chemvue app over Spectrometry. So go check it out, pasco.com/Chemvue. Now we briefly talked about saturation. The more double bonds there are, the more saturated the compound is. On the left here, you've got a single or a one double bond. On the right, there are two double bonds. So we've got more this is more saturated on the left. This is less saturated on the right. So it's a little bit more unsaturated. We got a double bond and a single and a double. So we got an alternating double bond. And look how much more bent the molecule is. So not only is this going to be more chance that it's a liquid, but it also is going to be more chance that it's not going to be transparent. Why? Well, let's take a look. Let's take a look at the UV-Vis spectrometer to help us figure that out. Okay, so I have got some, do a calibration here with, I'm just going to use distilled water. Uh-oh, I can't find my calibration. You bet. Let me see if I can locate that. There it is. Okay. So I'm going to calibrate. And same thing here, we've got the light and the detector, straight path through here. So I want to turn the micro cuvette. Let's see if I can get this. Sorry, I didn't switch my camera. We're going to turn the micro cuvette so that the 1 centimeter path length is the path that the light goes through. Let me switch to that. There. And calibrate. Calibrate dark. Calibrate light. And we're going to be looking at these substances, these oils. This is mineral oil. They're all at one point came from plants. Mineral, right? Because petroleum was at one time largely plants. It's very old and very refined plant stuff. This is canola oil, soybean oil, extra virgin olive oil, and sesame oil, which keep in mind, sesame oil is made from toasted sesame seeds. Look how dark it is. So clear to dark. And let's see what the path is, what the pattern is with our UV data. So here's mineral oil. Okay. Mineral oil. Okay, my if you gotta go, I'm kind of up on time, but I'm got maybe 3 more minutes left. And you'll receive the recording when we're through. Anyway, so this is mineral oil, followed by the next clearest one. This one is canola oil. And I can check box. Look, I can turn runs off and on individually. That's another advantage of Chemvue. And we can see that it's shifted to the right a little bit compared to mineral oil. So it's a little bit less clear. Now soybean oil, I can start to see some yellow in there. Definitely getting some color now in the oil. Soybean oil is even a little bit more shifted to the right. And then extra virgin olive oil. Check it out. We can see the chlorophyll wavelength in that extra virgin olive oil in addition to the same signature we see in the other oils, but there's the chlorophyll and we know that that's good olive oil. And again, more dark, the more double bonds. If you look at those molecular structures, you'll see that pattern. This is the toasted sesame oil. Question. Go ahead.
Do we have time to see the fiber optic cables?
Yes. I'm gonna. So if you need to leave, go ahead. I'm going to demonstrate them next. So we're going to look at the fiber optic cable and also the flame test, and it takes just minutes. So we're going to talk about light emission. And for this, we're going to have to turn the light off. And I'm going to quickly talk about my setup. You're going to see the light go off again in a second. So this is the quartz fiber optic cable. It has a notch on one end so that you know how to orient it in the spectrometer. I've got the fiber optic cable pointing at a hydrogen lamp, and I'm going to turn the light off, turn on my light source. I've got the fiber optic quartz cable pretty close to that, pretty close but not touching the light source. Let's go to the light and start recording data. And I must have bumped it when I got up because it's Not showing up, so I have to realign it to make it show up. And help me know when it's showing up because I can't look at both at once. See it yet? Oh, I think I saw a little bit of it. So yeah, I got a little bit of bumps here. I'm working on my alignment here. Yep. There. Okay. All right. So now what I can do to improve the signal is I can set the integration time. And what that does is it helps determine, well, that's really not a powerful light source. And look at it helped readjust the intensity to what I've got in my data. And I can hit stop now. And I'm going to change out of dark mode and maybe we could see a little bit better in light mode. I could also, there's a pink. I can turn off the light source since we have good data now. Okay. I can also go to the manage runs and change the color that way. So we can look at the reference here because we can see some emission in the red and the light blue and the blue and choose hydrogen from the source because that's the first one. And that happens to be what it is. It lines up perfectly with hydrogen. You could go through all the other elements that show the emission lines with these given. And I did do a neon, or not neon, sodium birthday candle in a quick video that I'll show. And I'll talk quickly about the setup. Interesting, it's not letting me put the video on there. Before I go to the video, you can snap the coordinate tool onto the peaks. Out of the way. And you can do this to more than one peak so that you can see. You also have some tools to shift the calibrate wavelength. If you've got a leaky or contaminated discharge tube, you can always shift the wavelength using that tool there. Let me move out of here. And like I said, the fiber optic cables are not interchangeable, but I did there are flame tests are kind of hard to do because you have to have a really stable flame to do it. And you pretty much have to not get your cable in the flame and make sure you don't melt it. This is a picture of the spectrometer setup. And it looks different than the setup you saw for fiber optic because it's a different cable. So anyway, let me try and get this video going. If you get a birthday candle that the orange ones burn orange because they are sodium, and on the reference, you can get a very small signal to show up if you use the integration time. Mine, you could see on this screenshot of it, mine was set pretty high in order to get that flame, and it was in the dark. But this is how you would use a magnifying glass to get more of the light into close to your fiber optic cable without damaging it. Right, to get help, you just go to the help.pasco.com/spectrometry or go to the link in the software in the hamburger menu at the top left. In Chemvue, it's in the modules at help.pasco.com/Chemvue. There's a spectrometry guide at pasco.com/products/guides/spectrometers, and it talks all about the 2 spectrometers we have and how everything works and what all kinds of accessories you can get and experiments we have, some of them. Please contact your regional PASCO rep if you're interested in any of the equipment you saw today. Thanks again for your attention, and thanks for hanging in there.